All right, boys and girls, today we are doing the lecture on absolute convergence test. And we're going to try to explain what this word means, the conditional convergence. All right, this deals with this classical series and other series like it. The thing that's classical about this is the fact that it is the alternating harmonic series. It goes like this. When you plug in -1, you get -1/1. Plus, when you plug in 2, you get -1 squared over 2, plus -1/3, plus 1/4, plus -1/5, etc., etc. That right there is called the alternating harmonic series. And it's called this because it's very, very much related to this series, 1/n, as n runs from 1 to infinity. This one looks like 1/1 plus 1/2 plus 1/3 plus 1/4, and so on and so forth. This one is almost identical to this one, except of course you've got the alternating signs on this one, which you don't have on the regular harmonic series. Now it's well known, you can use integral test, for example, to show that this one diverges. If you keep adding these numbers, you'll go all the way to infinity. And it's well known that this one converges by alternating series test, which is one of the ones we've done before. So when this happens, the relation between these two is, if you call this one, let's say we call this one AN. So suppose we call AN -1/n. So that's my AN. If I look at the absolute value of AN, that would be the absolute value of -1 to the n all over n. That would just be 1/n. So the relationship between the alternating harmonic series and the regular harmonic series is that the harmonic series is the absolute value of this one. Absolute value just cleans up all the negatives. And we're going to learn an important test that has to do with the relationship between the convergence of the regular series and the absolute value version of that series. I mean, right off the bat, you can clearly see that the one with absolute values will always be larger than this one, because this one is adding some and possibly subtracting some items. So this sum will always be smaller than this one in absolute value, or less than. So here we go. The convergence test says that if the absolute value version of it converges, then you're done. The original one converged. And when that happens, we call the series absolutely convergent. Okay? We call these series, this one, absolutely convergent. Okay, and that's kind of important because they'll have very, very special properties when the series is absolutely convergent. Amazing properties, which we'll get to later. But if this one diverges, but this one converges, in other words, this test failed, then we will call this one conditionally convergent. Okay, we'll get to that later. Or we can try it right now. If this one diverges, but the other counterpart, this one, converges, then we call our series, we call it conditionally convergent. Let's just abbreviate it, convergent, okay? If one converges and the other one doesn't, then it's called conditionally convergent. Clearly, if one converges and the other one diverges, this is the one that's going to diverge because that's the larger one. So if only one of them converges, it's called conditionally convergent. If both of them converge, it's called absolutely convergent. Okay? Now let's take a look at this amazing example. So if we start to write things down here, as I plug in the first item here, I'll get 2/2. This will be 1. So with a 1 here, this will be a 1. And a 1 there, so the whole thing will be a 1. So this will be -1/1 squared plus. As you plug in 2 here, 2 here, and 2 here, this will be a 3. So this will be negative 1 to the 3. That will give us, again, negative 1 over 2 squared. As you plug in 3, that will give us 3 plus 1 is 4. This will be an even number, making this a 1 over 3 squared, and so on and so forth. So you see the pattern is quite clear. What it's doing is alternating signs, but 2 at a time. You go negative, negative, positive, positive, negative, negative, positive, positive. The question is whether or not that converges. Well, the absolute convergence test says, hey, check it out. What if we just got rid of all these negatives altogether, this sort of noise altogether? And so what if we consider just the absolute value of negative 1 to the n times n plus 1 all over 2 all over n squared? That would be equal to just 1 over 1 squared plus 1 over 2 squared. All of them just be 1 on the top. That would just be equal to the summation of 1 over n squared as n runs from 1 to infinity. Clearly, the basal problem that will give us pi square over 6 clearly converges. And so, by the way, that's thanks to Euler. So this one with the absolute values gets rid of all these annoying alternating signs, and it makes it actually a super, super easy problem. You don't even have to know this much. You don't have to be Euler. You can also do it by integral test, for example, and you'll know that this converges. So the point is that by getting rid of all these negative signs, we got something that was much, much simpler. We can see that this one converges. Therefore, what can you say? Well, you can say that if the absolute value converges, then the original one converges. And so the summation of negative 1 to the n times n plus 1 all over 2 all over n squared also converges. And we're done. We proved it using the absolute convergence test. That's how you do it. Basically, you get rid of all the negatives, annoying ones, and see if you got something easier, something that you can handle. And if that's the case, you're done. It converges. If this one had diverged, then all bets are off. This doesn't tell you anything if this one diverges. The condition to apply this one is this one has to converge. If you meet the condition, then you get a result. If you don't meet the condition, you can't say nothing. Okay? So let's take a look at this one. Again, you've got here, if you were to write it out, you got negative 1 to some power here, 0 over n to the 6 plus negative 1 to the 0 all over n to the 6 plus negative 1. This is a 0, this is 1, this is 2, would be 8. 8 minus 2 is 6, all over n to the 6, and so on and so forth. You got all sorts of crazy things happening here on the exponent. The alternating series test says, hey, forget about that. Let's consider the absolute value. So if you have the absolute value of negative 1 to the n to the third minus n all over n to the 6, that cleans up the whole thing. It just becomes n to the 6, which is super easy, for example, by the integral test, converges. So therefore, the original one, this one right here, converges. And you're done by the absolute convergence test. That's how that works. Okay? All day long, every time you want to get rid of these negative, some strange pattern of negatives or whatever, negatives and positives, always a good one to go to is the absolute convergence test. Okay? That one's the same thing. Let's try this one. This one's even more annoying because you've got a cosine of some sort of number of radians here. Whoops, where'd that happen? What happened there?